Okay, at last, part 4 of this video on PCA for regression, and in previous parts, what we looked at was orthogonal regression, right, and its applications, possible applications maybe in finance. We discussed a couple of important points about orthogonal regression, one of them being that it can be useful, or it should be considered when you're thinking of a regression where the variables are entering in equal relationship, where it's not like one of them is independent, the other one is dependent, and so on. It's more like both variables are probably dependent on some other hidden variable which we do not observe, and we might be interested in it or not. So we said in those cases we could consider orthogonal regression, and that was the main point of this video, to sort of equip you with this new tool. Then at the end of part 3 we focused on the following point. We said even orthogonal regression for the problem which we looked at in the beginning, which is a paraglider, right? We saw this paraglider data, right? And we started the whole conversation with saying that ordinary least squares regression wasn't producing a reasonable fit, that it seems like it should be some vertical line, and then we said orthogonal regression seemed to address it, and we said the reason because it seemed to address it is because the latitude and longitude data which we looked at was generated by some underlying process which could be quite complex, some other factors which are hidden, which we do not observe, and they're defining latitude and longitude, and that's why latitude and longitude are equal, and PCA seemed to work. But it was a patch, really. It wasn't a total solution, and the reason why it wasn't a total solution, because we said what? We said the model should match DGP, and it didn't. Even PCA wasn't really matching the DGP, just happened so to work in this particular case because the wind was maybe constant speed and direction and so on. So in the end of part 3 I promise that we will actually try to build a realistic model which would much better reflect what's going on underneath, right? And that's exactly what we're going to do now in part 4. So if we analyze the data, we could see what's going on is the following. We have this paraglider. It starts at some point right in the beginning of our data set, and then it's circling in the air. So it's, imagine like if it was connected to some kind of a center, and then it was circling around it. So it starts circling in the thermal, but then there's a wind which is blowing from south to north, maybe a little bit to the east, right? Northeast. And that wind is moving the center around which the paraglider is gliding. And that's why we see the spiral-like data structure. So when we did the PCA, what happened was that this PCA regression, it captured the direction of the wind. It's because your data is moving in northeastern direction. Most of the variation is along this axis, and that's what PCA is probably picking up. But we can easily see that the actual movement is a little more complex, right? So what we're going to do next is we're going to, as a first step of our problem solving, we're going to convert the latitude and longitude into Cartesian coordinates, x and y. And by the way, this part involves some geometry and trigonometry and other interesting things which are, I will say, optional. So if you're in finance field, you can skip this whole part 4. But it could be interesting to see how the model building works, right? So what we're going to do is we're going to convert longitude and latitude into x and y in kilometers. How are we going to do it? Well, latitude is somewhat easy, right? You get this latitude and multiply by radius of the Earth, basically, and then, well, you have to first convert it into radians, and then multiply it by radius of the Earth. With longitude, you have to do an extra step, and the extra step is the following, because a longitude is measured along the meridian, right? And meridian, if you see on equator, is much longer than meridian when you start moving closer to the pole, where meridian becomes zero length. Meridian is a circle, like this on the surface. So we have to adjust for decreasing radius of the meridian, and that's done by this cosine formula, and it's all geometry, right? Phi here is the latitude, and lambda is longitude, right? So that's what we're doing here, because longitude is along the meridian, and then we have to adjust for the radius of the meridian. That's what we're doing here. Okay, so once we've done that, we got the coordinates in kilometers, or meters if you want, but I did it in kilometers. And right, I'll remove that later. Now, next we will run a principal component analysis on x and y, on kilometers variables, and once we got that, we will draw PC2 as a function of PC1, and now we see it becomes this horizontal line. Remember in the beginning I said all the or most of the variation is along PC1, principal components 1, and some of it around principal component 2. So if we now draw the principal component 2 as a function of principal component 1, you will see the spiral-like movement, right? So now that's what we're trying to model. Okay, how can we model the spiral? This is how we could do it, right? So this is another view of the same principal component 1 and 2. So here I am drawing a number of observations, 0 to 122, right? I'm saying it's time. I'm assuming it's like second or minute, doesn't matter. But let's say it's some unit measure of the time. Now, the blue line is PC1, and the orange line is PC2, principal component 2. So you see the blue line has a slope, and that's wind, right? Because your principal component 1 is not just staying at the place, right? It's moving to the right side. And that's what the slope of the line is, the wind, right? So the slope here is the speed of the wind. Look, we immediately, we actually solved the big part of the problem of the poster of that problem on stack exchange, which we looked at, which we started looking at part 1 of this video. The poster was interested in maybe in the speed and direction of the wind, right? Here's your speed of the wind, 4.3 meters. So it's in kilometers, so it's 4.3 meters per whatever is the sampling interval. So if you're sampling every second, every observation was the next second, that would be 4.3 kilometers per second. Oh, that would be a lot, right? 4.3 meters per second. That's pretty good wind, right? So that was your wind right there. What else? Well, now let's think of the equations for principal component 1 and principal component 2. We could say principal component 1 is a horizontal movement, so this Vt is the speed of the wind multiplied by time. That's how the center of the movement of this kind of movement is looking like, right? So the center is moving at constant speed v to the right, and then paraglider is circling around the center clockwise at the radius r, at some frequency, right? Frequency and radius. So while center is moving, you get this spiral-like movement. So The principal component 1 is the equation I wrote for this type of mechanical movement. Why did I move it? Right. And principal component 2 is simply rotation. So there's no it's like rotation in place pretty much, right? It's on y-axis, and that's a sine. This is a sine, this is cosine, right? PC1 is cosine plus the movement in time. So once we have these equations, all we need to do is just minimize sum of squares. So that we could do in a simple way, but we decided instead of just minimizing it like in a straightforward way like this, it's better to do it step by step. Like for instance here, we already know what's the speed of the wind, right? We can find out what is x0 and y0 in these equations. Just simple regressions which we had on PC1 and PC2 already gave us a lot of parameters. So x0 is known from the regression of PC1, y0 is known from regression of PC2. These are the intercepts. Speed of the wind we got from the first regression, right? How we find the radius though? Well, to find the radius, we do the following. We get the PC1 and PC2 graphs like here, but then we detrend PC1. We remove this slope, right? And when we detrended it, we see they look like two sine waves, right, with shifted phase. And they're reflecting this circular movement with the same radius. So they have the same radius. And what we could do, we could square the PC1 and PC2, detrended PC1 and PC2, and some of those squares will be squared radius. So from just getting the average of this gray line radius, we can now find the radius. So if you look at this equation, we already know x0, v radius, y0, and this radius we already know, and what's not known is the frequency of rotation and the phase. Those are not known, and those we can find how? Through phase analysis, right? So when we found the radius here, all we did was the following. See, the detrended PC1 was just the cosine, and detrended PC2 was just r sine, right? So that's what we did. We got PC1 squared, like this. PC1 squared plus PC2 squared was equal to what? R squared. Trigonometry will work out, right? If you look at this formula. That's how we found r from here, right? Squared. It should be a constant, so we just get the average r squared and then get the square root of it. That was one. That was r squared. But then look at this part though. So if you take PC1 and divide by PC2, that is your tangent. I think it's tangent. Let's see. Actually, it's PC2 over PC1. I knew it, right? So if we get the PC2 over PC1, that is going to be a tangent of what? Of 2 pi frequency, right? Plus the phase. Which means if we get arc tangent of this quantity, right? If we get arc tangent of PC2 over PC1, then we get a linear equation. Actually, there has to be t here, right? Time. So we can regress on time. We can regress arctangent of principal component 2 ratio to principal component 1, and we will get this regression. And that's exactly what we got in this picture. And when we do that, we can find the both the frequency and the phase.